Welcome to homework.
Question number 86, the last question of the chapter and the longest. We'll start with the basics. The definition of standard enthalpy combustion is the enthalpy change for 1 mole of substance that burns or combines with the oxygen under standard state condition, that is 1 bar pressure and 298 Kelvin temperature. For part A, assuming that the natural gas is pure methane, therefore the heat provided is 3500 kilowatt with 89% furnace efficiency. Determining the amount of heat provided by methane into kilojoules, we can calculate it as 1.26 into 10 raised to power 7 kilojoules. But as the efficiency of gas furnace is the percent of heat produced by the combustion that is transferred into the house, therefore, it is decreased to 1.42 into 10 raised to power 7 kilojoules. Therefore, calculating the number of moles of methane required to produce this amount of heat, we can refer to the table for standard heat combustion provided into the textbook. That is negative of 890.8 kilojoules. So the number of methane required would be 15,940 moles. Okay, that's quite high. After calculating the number of moles of methane, the total mass of methane can be calculated. Substituting in the values of, okay, we can calculate the number of moles, that is mass by molar mass. So the total mass of methane turns out to be 255,700 gram. That's a lot. Now, substituting in the value of density of methane and the mass of methane, we can calculate the volume of methane in liters. That turns out to be 375,500 liters. We can convert the above volume of methane in liters into cubic feet using this correlation. So the volume in cubic feet turns out to be 13,260 cubic feet. For part B, as the heat produced by combustion of gas that is transferred into the house is already calculated, which is 1.42 into 10 raised to power 7 kilojoule. Assuming that the LPG is liquid propane, we can again refer to the table and we can have the heat of combustion that turns out to be 2219 kilojoule per mole. As the last time, we can calculate the number of moles, which turns out to be 6399 moles. Substituting in the values of molar mass and number of moles of propane into the given equation, which is represented over here, we can calculate the total mass of propane required. That turns out to be 28,200 grams. Using the density mass relation, which is represented by the equation over here, we can calculate the total volume that turns out to be 53.07 liters. We can turn that liter into the gallons through this correlation. It turns out to be 141.2 gallons. Considering the following reaction of methane, which leads to formation of 2 moles of water and 1 mole of carbon dioxide. According to the reaction, same amount of carbon dioxide is produced by combustion of methane. So the total mass of carbon dioxide produced can be calculated as follows. Substituting in the value for molar mass of carbon dioxide, number of moles of carbon dioxide into this formula over here. The total mass of carbon dioxide produced is 701.52 kilograms. Next, considering the following reaction, methane plus oxygen leads to carbon dioxide plus water. So, according to the given reaction, the amount of water is twice the amount of methane. Therefore, number of moles of water will be twice of methane. That comes out to be 31,880 moles. Substituting in the values of water into the given relation, we can find the total mass of water produced. That is 574.32 kilograms. That's a lot of water. Considering the following reaction of combustion of methane, as the number of moles of methane required is already calculated in part A, which is 15,940 mole, we can calculate the number of moles of oxygen required, which turns out to be twice of moles of methane, that is 31,880. Substituting in the value of mass of oxygen and number of moles of oxygen into this relation, we can have the total mass of O2, that is 102,0160 grams. Now, as only 23% of air is oxygen, therefore the overall mass of oxygen is as follows, which is 443,5478.26 grams. Substituting in the density of propane and mass of propane, we can find the volume of oxygen or mass of oxygen, which turns out to be 363,5637.92 liter. This volume of air is required to provide oxygen for the combustion of methane to heating a house. Last part, the F. As the electricity is 100% efficient in producing heat inside the house, therefore, the amount of heat required would be same as 3,500 kilowatt. The part G. As the efficiency of production and distribution of electricity produced in coal-fired plant is approximately 40%, therefore, we can use the unitary method to find 8750 kilowatt of energy is transferred. The mass of coal required can be calculated as represented over here, which turns out to be 3,872 pounds. This mass of coal is in pounds, but the mass of coal required is in kilogram. So there's a correlation between pound and kilogram, which is represented by this. Using the common unitary method, we can convert pounds into kilogram. That turns out to be 1,756.34 kilograms. This amount of coal is required to produce the electrical energy necessary to heat the house if the efficiency of production and distribution is about 40%.